Let's be real, who hasn't watched Star Trek, seen the Enterprise just zip away at warp speed and thought, man, could we ever actually do that? For decades, it's been the ultimate sci-fi dream. But what happens when that awesome dream smacks right into the cold, hard laws of physics? Well, today we're going to trace the incredible journey of the warp drive, from a total TV fantasy to, believe it or not, a subject of serious scientific research. Okay, let's get into it. So first up, I just want you to look at this number, 75,000 years. I mean, that is just a staggering amount of time, right? What in the world could that be? Well, it turns out this number is the whole reason we even need to dream about something like a warp drive in the first place. That's right, if we wanted to send our fastest probe, the amazing Voyager 1, to our closest stellar neighbor, we'd have to wait 75,000 years for it to get there. The universe is just mind-bogglingly huge. It makes traveling between stars with our current tech pretty much impossible. So to really explore the galaxy, we need a much, much better idea. And for a long time, the best idea we had came straight from science fiction. To solve this colossal problem of distance, the folks behind the Star Trek came up with one of the most iconic pieces of tech in sci-fi history. It's an idea that completely defined what humanity's future in space could look like. And you gotta understand, the warp drive in Star Trek, it was way more than just a cool special effect to get the crew from point A to point B. It was a symbol of progress. It was the key that unlocked the galaxy and allowed humanity to boldly go where no one has gone before. The entire franchise, really, runs on this one engine. And in the world of the show, they built this whole history around it. In the year 2063, the Sky Zephram Cochrane makes his flight, and it literally changes everything. It triggers first contact with the Vulcans. Then you fast forward a few hundred years to the 24th century, and warp drive is just normal. It's like catching a plane, letting ships like the Enterprise cruise across the galaxy. But that's fiction. What does reality have to say?
Back here in the real world, there's this huge wall standing in our way, a cosmic speed limit, if you will. And the person who put it there? None other than Albert Einstein himself.
This is the big one. General relativity tells us that space and time aren't separate things. They're woven together into this fabric called space-time. And the rules of that fabric are super strict. One of the biggest rules is that nothing with mass, you, me, a spaceship, can accelerate through space past the speed of light. It's not a technological challenge we can overcome. It's a fundamental rule of how the universe works.
This is a fantastic way to picture it. Think of space-time like a big, stretchy bedsheet. A massive thing like a star doesn't pull a planet towards it. It just bends the sheet, and the planet is just rolling along the curve. This ability for mass and energy to bend space-time is absolutely key. For decades, it seemed like a dead end for FTL travel, until one physicist, who happened to be a huge Star Trek fan, found a loophole.
So if the laws of the universe say you can't go faster than light, what do? Well, you don't break the rules, you find a loophole. You get clever. You find a way to bend them. Literally. Meet Miguel Alcubierre. And get this, in the early 90s, he's watching an episode of The Next Generation and he starts thinking, what if the warp in warp drive was literal? What if you could actually warp space-time? So in 1994, he publishes this incredible paper that took the warp drive out of the world of sci-fi and dropped it right into the lap of theoretical physics. Okay, this is the absolute key to the whole thing. Pay attention here. Einstein's law says you can't move through space faster than light. Fine. But what if you moved space itself? Turns out there's no known speed limit for how fast space can expand or contract. We know this for a fact. Right after the Big Bang, the universe expanded way faster than the speed of light. Alcubierre's genius was to ask, could we create our own tiny controllable bubble of that expansion? So here's how it would work. Your ship is just sitting there, totally still, inside a little bubble of normal space-time. Then, the drive kicks in. It squishes the space in front of the bubble and stretches out the space behind it. The bubble gets carried along on this wave, kind of like a surfer. Inside the bubble, the ship isn't moving at all, but the wave itself can travel at, theoretically, any speed. You're not breaking the speed limit, you're just riding a ripple in the road. Okay, I know these charts look like they're from a physics final, but the idea is actually pretty straightforward. The plots on the left show the effect. That big dip is space getting squeezed, and the hill is space getting stretched. The plots on the right show what you'd need to create that effect, a very specific kind of energy field. Mathematically, it was perfect, a beautiful solution, with one tiny, universe-sized problem. Alcubierre had basically given us a roadmap to the stars.
But the fuel required for the journey was something that, well, something that seems to violate everything we know about physics. The math worked, but the ingredients were, let's just say, exotic.
Here's the massive catch. To make that space-time bubble, the equations demanded something called negative energy or exotic matter. This isn't antimatter, which is real. This is theoretical stuff that would have negative mass. It would fall up. As far as we know, it just doesn't exist. It's the scientific equivalent of being told your car will run, but only on the power of a magical unicorn.
Oh, and it gets worse. You didn't just need a little bit of this unicorn magic. The first calculations showed that to make it work, you would need an amount of negative energy equal to the mass of the entire visible universe. Yeah, not exactly practical. This was the showstopper. It made the Alcubierre drive feel like a cool thought experiment, but ultimately impossible. But here's the cool part. Scientists didn't just give up. People like Harold Sonny White over at NASA kept tweaking the math. And they found that if you change the shape of the bubble, making it less like a thin shell and more like a thick donut, you could slash the energy requirements. It went from the mass of the universe all the way down to the mass of something like the Voyager 1 probe. Still an impossible amount of imaginary energy, but hey, it's a huge improvement. So this is where we're left. A brilliant loophole in the laws of physics, but it requires an ingredient that probably doesn't even exist. So is that it? Is this where the story ends? A cool idea, but just a dream, forever stuck in science fiction? Well, not quite, because just very recently, the story took another surprising turn. A whole new generation of physicists started looking at the problem in a new way, and they've come up with something pretty startling. This is the breakthrough. This is the game changer. New models, some published just this year, have found ways to design a warp drive that works entirely within known physics. No negative energy, no exotic matter, no magical unicorns.
So it's the catch this time, because there's always a catch, right? This table lays it out perfectly. The classic Alcubierre drive could go faster than light, but it needed that impossible negative energy. These new physical models use normal, conventional energy, which means they are actually possible, at least in theory. The trade-off? They're subluminal, meaning they travel slower than the speed of light. So we're basically trading faster than light for actually possible. And I think that's a pretty good trade.
But don't let slower than light fool you. We are still talking about a warp shell that could propel a ship way, way faster than any chemical rocket we could ever build. And this isn't just scribbles on a whiteboard anymore. Scientists are actively building computational tools, like the Warp Factory, to design and test these new, physically plausible warp drives. The impossible sci-fi dream is slowly turning into a real-world engineering problem. So, what a journey, right? We've gone from a TV show to a cosmic speed limit to a brilliant loophole with an impossible price tag, and now, finally, to a design that might actually work. The path from fiction to fact is never a straight line, but for the first time in history, the warp drive is starting to feel less like a what if and more like a how to. The question may no longer be if we can do it, but simply how.